Welcome, everyone. On behalf of Power Transmission Engineering, I'm honored to present another in a series of educational webinars for the gear industry. I'm Gary Jesch, your moderator for this webinar today, and it's always great to have you join us for important webinars about the gear industry and its business leadership. Before we get started, we want everyone here to know that we will be answering questions at the end of the presentation, so feel free to use the questions tab in the GoToWebinar control panel, and we'll get to as many as we can by the end of the presentation itself. Others will receive responses offline from our presenter, and you're also welcome to contact him directly via his email, which we'll provide at the end. Additionally, we're recording this presentation and we'll be making it available as an on-demand video within a day. So here's some info about today's program. Gearbox failure means unplanned outages, downtime, and potentially extensive repairs. With the right evaluation approach, it can almost always be avoided. But if your gearboxes were nearing failure today, would you know? Let's learn what it takes to avoid gearbox failure in this webinar, co-sponsored by PTE and Philadelphia Gear. 17-year field service veteran Herb Cobb is here to give you the knowledge to spot early signs of gearbox failure. Herb will be taking a look at common and uncommon failure causes, the largest factors in operating conditions, online and static evaluation methods, when to look further, and when to take action. Herb's Philadelphia Gear on-site technical services supervisor and project manager, having overseen support, evaluation, installation, alignment, startup, testing, and repair on industrial gear drive systems since 2004. Prior to joining Philadelphia Gear, he worked on construction and commissioning projects for Siemens Westinghouse gas turbine units, and he also served as a machinist mate in the U.S. Navy for more than a decade, operating and maintaining gear and generator systems on aircraft carrier platforms. So with that said, how do you do there, Herb? Welcome aboard. Are you ready to go?
Yes, Gary, it's an absolute pleasure. Thank you very much. Good morning, ladies and gents. Like Gary said, we're here to discuss gearboxes and what we need to do to evaluate and understand our gearboxes that we own and operate. We need to think about the quality of our gearbox, not only the quality of the design, which is based on truly understanding the process that the gearbox is serving and the application that the gearbox is providing. The quality of that design is crucial. We also want to talk about or think about the quality of manufacturing. Now, the American Gear Manufacturing Association, the AGMA, sets the standard for evaluating the quality of gears. So we can think about the ideal design, the geometry that is on the table, on the design pad. How closely do we match that design? If we're extremely close to the tolerances in all those geometry factors, well, that's a high quality gear. And we can think of the AGMA quality as well, it's actually assigned an integer number. The highest quality gears are 15, but that's very highly specialized gear sets that operate at high speeds. Typically, in low speed applications will be 8 to 11 is the gear quality number. Now, if we've got that very formal attitude about quality on the gear manufacturing, we ought to also consider that we need to have high quality installation, operation, and maintenance of our gears. And that's where we, as the owners and operators of gear sets, can come into the picture and provide that. Basically, gearboxes are designed to serve a function, and the ability of every component within the gearbox to perform its function is closely related to the lubrication that is provided to that gearbox. So frankly, a lot of the failure modes that we see are related back to the lubrication and issues with that lubrication. Once we have issues with the oil and how it's provided and how it's able to cool and lubricate its components, if there's a degradation in that performance, well, that's when we actually have bearing and gear failures. So when we talk about the most common component failures, most of them have to do with lubricant, a lack of lubricant, a lack of flow, contamination, or somehow a degraded condition or incorrect lubricant. Other factors that lead to gearbox failures are when we have abnormal or unanticipated forces applied to our gearbox. Also, you can see there overloads, misalignments, fatigue failures, or combinations of the above. Now, there's a few things that we typically need to do before we go out and formally evaluate a gearbox. One thing is you need to know a little bit about what you're looking at. So one, understanding the role that that gearbox is playing, the service that it is providing to your process or your application. By that, we need to understand the speed requirement of the driven load and the speed of the prime mover and how this gearbox is arranged, all its components, to translate that efficient operating speed of the prime mover down to or up to the efficient operating speed and power requirement of the driven load. Another thing we need to do is we need to look at the history of this gearbox a little bit. If it's a unit that's been in service for some period of time, we need to spend some time and evaluate previous evaluations and reports and understand the maintenance that has occurred to the gearbox since it's been evaluated last. Oftentimes, we in these modern days with changing requirements within our plants, we also have operational changes that affect our gearboxes, and we need to understand how changes like that may have affected our gearbox. One final thing that we need to do is review the actual technical specifications, review the technical manual and the drawings and procedures that have to do particularly with this gearbox. There's a few concepts that I like to keep in mind. I'm a big advocate for gearboxes. I've got the luxury of being motivated by technical correctness, and I have a fairly minimal concentration on the commercial aspects of the gear industry when I'm on site. I'm an advocate for the gearbox itself. You know how the Lorax speaks for the trees? Well, I speak for the gearboxes. So one concept that is absolutely vital is the fact that you can see it right here. Cleanliness is next to gearliness. I don't think that's in the Bible, but maybe it ought to be. See these photos right here? This is a time when just a tiny pebble, you can see it stuck in that orifice plate on the right, caused massive damage to a brand new gearbox. This gearbox was installed at a customer site, having just been reconditioned actually, but with a brand new set of rotating elements at our gear shop. It was commissioned, and the very next day I got a phone call from the owner operator of this thing, and they said, hey, guess what? The input shaft is turning, but the output is not rotating. We went out there and found out that, you see that top left picture, that's where their field lubrication system, it was a off-unit lube skid, which had a sump and a pump and a filtration and heating and cooling elements associated with it. That is the flange where their system tied into this brand new gearbox. And you can see that bearing cap behind it, basically all the paint burned off because there was a pebble that got into the system and got stuck in that orifice plate that supplies that top bearing You can see the bottom left picture. When that top bearing failed, obviously that shaft fell out of proper alignment, and it was a cascading casualty. So that little pebble was about $250,000 worth of heartache, all because of insufficient practices regarding foreign material exclusion. Okay, here's another concept that I like to think about and present. View every surface that you can when you're evaluating a gearbox. Tooth by tooth is what we say. We try to rotate and index these gearboxes so that without major disassembly, through the inspection ports, we're able to view as many surfaces as possible. This is an example of when we dropped a thrust bearing out of we lowered a thrust bearing, removed it from a bowl mill down in South Carolina during a rebuild process. That bearing looked not bad in the beginning, but we took the effort to actually index everything, and we saw all the surfaces, and sure enough, there was this massive failure of not only the cage, but a roller had just failed. That tapered roller failed massively. So view all surfaces is another concept. Also, kind of like that cleanliness one from before, find a way to do it clean. If you cannot make the surfaces and the surrounding area clean enough to open and evaluate a gearbox, just don't do it. Wait until you've got an opportunity to safely evaluate a gearbox without introducing a big problem into the system. Once it's in the gearbox, it's hard to get out. But if you maintain that barrier, you don't let these pieces of debris into the gearbox, you won't have to deal with it. Another concept, follow procedure. Well, this is an example. You can see, we all see these subtle little failures and degrades on disc type couplings. This is a radical failure that occurred because of an assembly error that ended up having bolts shear off and caused an imbalance and loose parts. And at 10,000 RPM, a major imbalance resulted in this. That picture of the bent shaft in the middle, it used to have the hub on the right mounted on that shaft, and that thing ended up through the side of the building and out in the parking lot because of an issue with compliance to procedural steps as this was assembled. Another concept, the Texas-sized blueprint. We got a lot of guys on our team from Texas, but nods to them, they're great gear guys. But the Texas-sized blueprint, the concept is, if you've got multiple or redundant systems, you can rely on those to be sources of information and feedback when regarding one of the units. If it departs from the normal operating mode of the adjacent units, well, you've got a lot to compare. So don't overlook that capability. You can always go to an adjacent unit, make comparisons. You can actually conduct some tests and experiments, not on the deranged unit, but on a perfectly operating unit. And just the concept carries forward. Don't overlook that as an asset in troubleshooting and maintaining and evaluating. When it comes to troubleshooting, this is the basic three-question sequence that I go through when I am trying to evaluate a condition. I do everything I can to understand some condition. And even though it may seem problematic, we really have to examine, do we actually have a problem? And if the answer is yes, then we have to ask ourselves, well, was there ever a time when this was correct? And if so, well, what has changed that led me from a good condition to our now deranged condition? The same questions apply also if you really don't have a problem. You've got some visual indications, maybe you've got several factors that are leading you to have some level of concern. You can carefully evaluate the system and those statuses, and maybe you can decide that no, it's not really a problem. This is a normal anticipated departure, so we're okay. And the fact is, there are many factors typically that contribute to any problem we've got. So that's good and bad. Number one, it's good because we don't have to correct everything. Maybe we can simply guide a few of the problematic factors back into the green range and arrest the development of the problem. I suppose the bad part is once you've got a problem developing, well, you've got a lot of things to solve sometimes to actually correct it. So let's think about going out to evaluate a gearbox. Typically, if you've got the opportunity, it's fantastic to evaluate the system during operation. When we have an operating unit, one thing I very much like to do is go out and take temperature and sound surveys. By temperature, take a non-contact thermometer and approach the unit and safely, avoiding any dangerous rotating equipment, safely survey all of the available external surfaces on the gearbox housing. And with this non-contact thermometer, these little infrared thermometers, you can find all the regions that are hot and the regions that are the highest temperatures and do your best to understand why. And I typically make a little set of notes. What are the external temperatures on the input pinions? What are the external temperatures on the sump, on the intermediate speed shaft, bearing caps, et cetera, et cetera. And you can evaluate those against prior results. When you're starting a system up or you're operating a system, it should come from its cold iron temperature up and eventually stabilize at a given temperature. So knowing those temperatures on the outside surfaces, a lot of these gearbox don't have a lot of embedded installed instrumentation. This is a way that you can actually get a number to hang on this status of the gearbox that's comparable to future sets of data. This is also the time when you can inspect for leaks, obviously, but it's a good time to take your vibration analysis readings as well. If you collect vibration data, you always want to do that in a very consistent way. The quality of your collection is going to aid you in the quality of your data and the quality of your analysis. Another thing that you might do is talk to the operators and see if they've had any issues. And if they report some sort of issue, this would be your opportunity to observe the problematic transients, whether they're startups or shutdowns or speed changes. You'll have that opportunity. So those are online checks you can do. Then we come down to offline checks. When the unit is static, everybody wants to simply crack it open and take a look at the gears. And I do think that's absolutely vital, but there are things that are often overlooked. In this particular case, if we look down to the oil system, that is one of the most problematic regions of these gearboxes that is neglected during evaluations. So the health and welfare of the pump, the filtration, the breathers, strainers, the coolers, all the different instruments that are associated with the oil system, these are things that require the same level of attention as the internal elements. So these are the beginning of our static checks. Then we actually move to some static checks that evaluate the health of the gears and the bearings and the shafting and the housing. There's a few different dimensional checks you might be able to take, not always available, but when it is available, it's preferable to compare these values over time. The axial infloat of shafting is something that will be directly correlated to where within the bearing set. So you can see on the left, we've got a dial indicator set up, and we would load that shaft axially away from the dial indicator, zero it, and then we would load it toward the dial indicator and check that total travel. You know, repeat that and then compare it to previous values, and you're going to be able to get a very good indication of how the bearing set is wearing or changing over time. That right photo is, you can see the dial indicator that's set up. It's measuring the very small bit of rotation that is available within the backlash of a gear set. That's the available radial movement, the available rotational movement between teeth. It represents the space available for one tooth to reside between two teeth of its meshing element. Backlash is prescribed, and it is measured when the system is cold, because when it heats up, some of that's going to go away due to thermal growth. The backlash on many gearboxes cannot be adjusted, but the gearbox that's depicted here does have adjustability because it's a spiral bevel set, and that's one of the key factors in properly setting up the gear mesh, is establishing proper backlash. Now, other static checks. We need to open this thing up and take a look at the condition internally. And you're going to see that some of these photos in the examples are sort of worst case scenarios, or at least examples of very bad conditions. Both of these are, most of these photos in the presentation are things that I've personally taken. That photo on the left, that's on a feed pump in a nuclear plant. So don't feel like some people are above having these issues. This was a condition that was a big surprise. This box had been opened and actually rebuilt 2 years prior, and suddenly this condition was found. It was the result of a lot of intrusion of moisture into this housing. Repeated heat up and cool down cycles allowed that moisture to be drawn in. That inspection cover on the right side, that's a marine application on a Navy ship, and they actually had a chloride intrusion into the oil system, and there was massive rust throughout that system. But evaluating those internal surfaces, be it the housing, shafting, available bearing surfaces, we want to take a look at those conditions, note them, and decide if we need to take action based on our findings. Another thing that's vital to do when you've got a gearbox that's idle, it may not be opened up. It may not be opened up and drained. So there may be oil resident in a sump down below, but what you can do is get a magnet and drag it along the bottom of that sump, and you'll be surprised what you find sometimes. Anything that's ferromagnetic is going to pick up. Examples on the left are kind of common small pieces of debris that have been lost off of gearing. On the right, this was after a tooth failure recently in a hydroelectric plant. Just a simple drag through, I found a big component section of a tooth, and that ended up having to be taken out of the system and rebuilt because it was a planetary arrangement, and those, once you have a gear failure, they tend to just spread all throughout the entire system. So this saved, finding this allowed us to take the unit out of operation and avoid cataclysmic failure of the unit. So let's talk about what do we want to see when we actually look at the gears themselves. When the gears are in mesh together, they ought to establish a pattern, an area where the work is being done between the driving tooth and the driven tooth. And we're going to talk about how that is formed and what we want to see. In order to do that, we're going to talk about the shape of the tooth. These modern gearboxes, very often you'll find that an involute curve as the tooth form. That is the shape that's formed. You can see how this taut line is unwound from a circle. It's unwound from the right, it's unwound from the left, and that forms the two sides of that tooth. That geometry is depicted here. We'll call that the involute form, that curve that is actually formed that shapes the tooth. There's a few terms that we can look at here. The addendum is the top half of that tooth. The dedendum is the bottom half of that tooth, and the pitch diameter that you'll see about mid-range on the height of the tooth is key to what we're going to talk about next. So there's this line across the flank of the tooth at that pitch diameter. We'll call that the pitch line. When these teeth that have the involute form are in mesh, we get continuous, constant velocity action and transmitting power. You can see that as in this particular instance, the gear that's on the left is the driving element. You can see that as that comes into mesh with the driven tooth, it starts to have contact low in the dedendum of that driving tooth. And that little blue line, the black dot in the middle of that blue line, represents where the actual contact and power transmission is occurring. It slides into mesh, and when it gets to the middle of that transition between the two, it's at that pitch diameter that we mentioned before. So we slide into mesh, and the friction between the two elements changes from sliding into rolling when it passes through that pitch diameter, and then it slides back out of mesh. So this is the involute meshing action. We want to minimize the sliding friction and maximize that rolling friction, because a lot of the power is transmitted at that rolling friction time frame of the mesh right there at the pitch line in the pitch circle. We talk about the power ratings of gears and talk about these two factors, strength and durability. Now, the durability is the resistance to wear, the resistance of that tooth to experience wear, and the strength is the resistance of the tooth for bending stresses to actually cause fracture and breakage of the tooth. Most designs actually have, we would rather experience wear before we experience breakage. And these are incredibly complex engineering calculations that go in to determine these things. There's like 18 factors for durability that are calculated in. But the fact is, those designs are based on trying to avoid breakage and wear. Now, let's just talk a little bit more about tooth geometry. We expect to have maximum amount of, the maximum amount of the tooth doing work as it goes through mesh and transmits power. We want the entire length of that tooth to perform work, but it's problematic to have a lot of forces applied to the tooth very near the ends or very near the tip of the tooth. So we actually modify the geometry of the tooth. We take it away from that perfect involute form. We actually, you can see crowning. That's the term we use for the amount that we remove material from the ends of those flanks to take the full geometry out of place, so we don't have a lot of force generated at those extreme ends. Also down below, you'll see that the involute curve is actually, we remove material to back away from that involute curve so we don't have a lot of force applied or transmitted at the tip of the tooth. It reduces breakage and wear. It also reduces noise and vibration generated within the gear mesh. So the contact pattern that shows how we're doing the work, we want to maximize the amount of the tooth that's doing the work, and this is what we want to typically see. There should be some indication, high and low on the tooth, of sliding friction, and the pitch line will see some evidence of rolling friction. That contact should appear across the entire uncrowned length of the flank, and it should be shared. If it's a double helical gear, we should share that uniformly between each helix. Now, on a brand new set of gears, it's going to be very difficult to see a wear pattern. This is a set that I put in 2013, and I've looked at it every 2 years since then, and you can barely tell that it's operated. So one thing we can do is actually do an unloaded contact check by applying this element on the left, this Dicom High Spot Blue. It's not a Dicom commercial, but they make a good product with lots of pigment in the carrier fluid. We apply that to our gear, and we apply some contrasting agent perhaps to the opposite gear that's driving, and then we run these elements through mesh, and we'll see transmission of bluing in the region that's in contact and doing work. And these are some examples of that unloaded bluing contact check that you can do. This is a single helical gear, 3 different examples that have satisfactory contact. And then you'll see on the left is a double helical gear in a marine application. Soft bluing was applied and transferred, and we've got pretty good contact there as well. And on the right, that's a spiral bevel gear. So the contact pattern we'd expect to see is different, and frankly, it's idealized. This is a very good contact for a spiral bevel gear. Now, you'll see that unloaded contact is not ideal because it didn't go across the entire geometry of that tooth. Only loaded contact will actually do that because the tooth tends to deflect and come into more full contact with its mate. So what we do is we apply those hard blue compounds a couple of slides back. You know, there's an aerosol or a paint on, and that hard blue is applied and allowed to dry, and then we operate the gearbox at full operating capacity and torque. And then when we shut it down next time, the area where that blue has been removed, well, that's our contact area. And you can see these are examples of good contact area that's being depicted. This is hard bluing, loaded contact. So that's another way we can evaluate it, even on a brand new gear set that really won't show us much. So there's a time frame when we've moved away from brand new gearing and we're starting to see some indications. So what are some abnormal things we're going to see? We're going to see evidence of abrasive wear, and we're going to see evidence of surface contact that is problematic. One thing we do get, because of that rolling friction at that pitch line, tiny geometries stand proud from the profile of these teeth, little asperites, and the oil film is very thin at this. The oil film is quite thin between gears as they mesh. We're talking tenths of thousandths in some cases, especially at the pitch line. When that compressive rolling force occurs, we will get breakages of any tiny proud geometries, and it will form, you know, the little high spots will break away and they'll be flushed out in the lubricant. And the remaining fractures down below is called micro pitting. Typically, this does occur. It's expected at the pitch line. You'll oftentimes get a certain amount of micro pitting. Here's another example of very small pits, very small pits, micro pits that have occurred. The little white dots that you'll see on this tooth. You'll see there's a couple of larger pits, but for the most part, this is a very stable condition with just a little bit of micro pitting. Sometimes the micro pits will form a region around that pitch line. You're starting to see that on the sort of the right side of these flanks. Why is it not all the way across the pitch line? In this case, load must be concentrated in this region. Could be due to just a little misalignment between the geared elements, could be due to some twisting deformation that's occurred that allows this area to be slightly more heavily loaded, and that very thin film allows this micro pitting to occur. Here's another example of, we can see an entire region at the pitch line, this band of micro pitting that goes all the way across these teeth. This is very uniform. I've looked at this gearbox many times. first time in 2004. And there's a couple of things happening here. Above the pitch line, you'll see that very polished region. That's some abrasive wear that's occurring in the addendum above that region. And on to the right side, just above the region of micropitting, you start to see an increase in the number and severity of larger pits. Pits will join up and form larger pits. If they continue to have regions that will come into contact through that very thin oil film. Now, this has been a pretty stable gearbox, and I haven't, I've had this level of concern, but it's been many years, and it's very stable in this condition. So on the left, micropitting, normal. On the right, this is when we've progressed into pitting, and this is problematic and needs correction. Here's an example of when micropitting has only really occurred after there was a failure of a bearing on an adjacent, on the other end of this particular cartridge that held this pinion in place. Because it has that misalignment, you see this abnormal wear pattern where that micropitting is developed. Classic sign of misalignment. The pinion had to be replaced after we corrected the misalignment in this particular case. Pitting. These pits can continue and join up with adjacent pits, and then it becomes macro pitting, and eventually spalling is another term we use for pitting that's essentially out of control and very problematic. These are elements that have essentially failed, and we really need to work toward a replacement at this point. Okay, let's talk a bit about abrasive wear. You might think, well, that's very highly polished and a very nice surface finish. Well, frankly, that has occurred because the lubricant has become filled with abrasive particles. This is called three-body abrasion, right? The tooth and the tooth that it meshes with are not actually coming into contact, but the very thin film of oil between them is filled with abrasive particles that are essentially making tiny grooves and removing geometry off of this tooth. It's happening here and it looks very nice, but it's problematic. It's because it's also occurring in every other surface within the gearbox that's served by that oil, including the bearings, and that's problematic. So that's abrasive wear in the form of polishing. This is another example of abrasive wear. You can see on the teeth on that bottom element, the dark line across the middle, right at the pitch line, sort of mid-height on that tooth, that represents the area of rolling friction. And we're not suffering a lot of pitting here, but above and below where the sliding friction occurs, because there's a lot of suspended particles in that oil, you're getting that region of abrasive wear. Now, here's an example of what we call adhesive wear. This is not three-element abrasion. This is actually two-element abrasion where the gears themselves are coming into contact. The oil film is very thin for some reason. Typically, the oil film is thin because we've had a breakdown in the oil quality, or sometimes it's because we've got mechanical overload of the system. For whatever reason, the high spots on these meshing elements are actually coming in contact with the adjacent tooth. It gets to when it makes contact, it actually has a little microscopic welding event that occurs, and then it instantaneously breaks free. That's why we see all this massive loss of profile and geometry. This is not a situation that is correct, or rather that you can live with. This is something that needs to be corrected pretty darn soon. Oftentimes, this is just something you track until it becomes necessary to change out the gear set. You track the progress of that over time, and you make part of your long-term planning changing out a gear set. This is where it's become very extreme. We've lost profile and we've got plastic flow because we're just in hard contact with the adjacent tooth. This is a gear that needs to be replaced. One of the things we said when we wanted ideal contact was that it would be shared between the helices, you know, the left-hand flank and the right-hand flank of a double helical gear. In this case, this is an example where we're absolutely not sharing the load. The flanks on the right-hand side of the screen are very lightly loaded compared to these poor flanks on the left-hand side of the screen that are carrying the majority of the load. Why did this occur? Well, one of these elements should be allowed to float axially so that it can simply follow the other and always be in correct mesh. In this particular instance, the bearings were set up incorrectly, and rather than be allowed to float freely axially, both of these gear elements were held axially, and they couldn't grow and move the way they should have. This ended up costing a gear set replacement, and we had to reevaluate how the gearbox was set up. And we had to make some changes, but now it's a very healthy gearbox. These are just some more examples. You see that picture on the left, same kind of thing happened as on the previous photo. One flank is heavily loaded and the other flank is essentially untouched. Again, that was a bad assembly, incorrect assembly that didn't allow axial floating. It's a very similar situation on the right-hand side. Another very common problem with gearboxes is corrosive wear. This is the development of corrosion that occurred. We think this one was actually chemically related, where an incorrect additive was put in the oil, and this corrosion just flared up all throughout the gearbox. This is another type of corrosive wear, corrosive etching, that you'll find sometimes. Sometimes these are not too progressive. This was due to long-term storage with no preservation. This is another corrosive wear situation where pits have developed. Again, this was a gearbox that was idle for a great length of time. It had to be hand dressed before it could be placed back into operation, and it's still gonna suffer premature death because it just didn't have proper layup and preservation when it was idle. This is another type of damage that you might see. There's electrical voltage potential that should not be present, but is, and it is making an arc across that very thin film of oil. And the one on the left, we'll call that fluting or tiger striping. That occurred at 1800 RPM. It was being driven by a turbine for about 3 days, and the noise from this gearbox just got worse and worse and worse as the surface finish degraded because of that electrical fluting. Then the gearbox was idle, but the electricity was still present. And you'll see down on the bottom of that photo, that is a section of gears that was in mesh when it was idle, and that still had that electrical discharge, and it just caused massive problems right there. This gear set was ground and corrected, but only temporarily. It was replaced 2 years later during the next availability. Similar situation on that right-hand flank, right-hand photo rather. Mostly these are electrical discharge issues are only present when there's some sort of a grounding issue within the system. As soon as you see this sort of thing, seek out and correct the grounds. Another type of failure mode or condition that you'll find is something that occurs. This issue on the left, there was just some inclusion in the forging for this particular piece. It was a material defect that existed before the manufacture of the part, and only later, after it had been in operation for some period of time, had that defect propagated cracks and eventually caused major fracture and released this big piece of this gear during operation that was operating at 3600 RPM. This one on the right, this is the bottom tooth that fractured out was a slow growth from a single little crack that propagated. When that tooth came off, it simply went through mesh, and the adjacent tooth was promptly fractured off just because of the massive bending forces applied with a big old chunk of steel trying to go through mesh. So once we've got our data, our temperatures, our photos, our condition, our vibration data, we want to try to effectively use that to plan the future. We need to look and compare our current status to our previous status. We want to look for negative trends. And it's good to actually, I like that note all departures from the ideal state. Even if you think something's not important, but you've noticed it, well, you know, we had some contaminant here, we had some degraded oil pressures and flows here. Mark that down and note that in the report so that it can be incorporated into our evaluation. The important thing is we make corrections to the very simple things that are easy to correct. And then we look at what have we been doing that has contributed to these conditions. We review how we operate and maintain, and we inform our long-term planning based on these findings. Another thing is to not based on our findings, but to carefully review action plans. If you're going to make a change to a system, really try to run it to ground. What are the potential downsides to avoid the law of unintended consequences? Like I said before, most failures actually have their root in a lack of lubrication. Something has caused these oil films to degrade or not be present, or not be enough flow to cool and lubricate the components that they're supposed to serve. Other failure modes we've talked about a little bit, but abnormal forces and conditions, well, when we're out of alignment, that's a big warning. These are various issues that can place us in a situation where the gear teeth are overloaded or the oil film is not present to the extent it should be. When we get down to the bottom line, root cause often has to do with us. We've introduced foreign material into the box, or we have incorrectly operated the gearbox, or we did our best, but the information given to us as far as technical guidance was incorrect. Maybe we renewed a bearing set, but we weren't given the incorrect bearing clearances, and we put them too tight or too loose, and that caused a failure. So that's basically the root of evil that we have to fight against out here in the gear game. When do we take action? Well, just very briefly, when our visual inspections show that there's a major shift or degrade in the contact. Also, when we pick up a lot of metallic debris in the sump, you saw it on those magnets, that's just a huge warning sign. We need to take immediate action. Now the vibration, if you've got good quality vibration data and you trend it over time and look at data sets that have been collected periodically, you can do this waterfall trending diagram. You can usually see increases in amplitude in problematic frequencies or establishment of fault frequencies from bearings. Those are a clear indication that we need to take action. Also, our oil analysis, we didn't really talk about that a lot, but absolutely vital that our analysis of oil occurs regularly and that we act on degraded system or situations that we find. Anytime we have a major event that overloads the mechanical system, whether it be the driver or the driven load, consider how that may have been transmitted back via the couplings into the gearbox, and make extra inspections and examinations based on that so that we don't have failures that have occurred or damage that's occurred and just not notice it. So at this point, I know that was just super quick, but it's an interesting topic to me. I love gears. I'll tell you what, Philadelphia Gear's been in the gear industry since 1892. I know you see Timken on the slides here. Timken has actually purchased Philadelphia Gear about 10 years ago, and Timken Power Systems owns owns a lot of different companies within the power generation and transmission field. So they wanted to have an excellent gear company, and they acquired Philadelphia Gear. Based on that, though, I am at this point open to questions, and it's been an absolute pleasure talking to you, ladies and gents, this morning. If you've got something that you'd like to reach out to me, my contact information is there. I spend every day in the field with gearboxes, pretty much year round, and I just absolutely love it. So.
Hey, well, thanks very much, Herb. Seeing these various, indicators through your eyes is a big help to people that have to do this type of analysis, and also the planning that goes along with it. So thanks very much. It was a great job. I really liked the photos. We do have some questions here for you. And to help us out, I'd like to introduce Rob Fisher, also of Philadelphia Gear. And Rob's going to help us. How's it going there, Rob? You online here with us now?
Doing well, and I appreciate everyone calling in to sit through the presentation.
Absolutely. Do you have a question from our audience there?
Yes, we do. So we have a user or a listener that submitted a question for Herb. He's referencing splash lubrication systems within gearboxes, and his question was about determining the optimum oil quantity and if that can be established theoretically or by experimentation, and what your recommendations would be there, Herb.
Okay, as far as level of oil within a gearbox that's splash lubricated, that means that some of the rotating elements are actually dipping into the oil and flinging oil so that it is distributed sufficiently within the unit. Most designs have this has been well considered ahead of time, and the exacting level of oil required in the sump at the time of design is either included in the technical documents or happens to be evident because the gear housing or the case usually has a sump level indicator right at that level where you could screw in a bullseye, and the oil level ought to be right in the middle of that level. Now, if you don't have any of those indicators, it depends a little bit whether or not there's an oil pan under the bull gear or not. The thing that we want to do is have sufficient oil being flung in the gearbox to do the task, but we don't want so much churning and activity of that gear down in the sump so that we get a tremendous amount of aeration into the oil. So by experimentation is a good way to do it if you're forced to. I would probably err on the slightly high side initially and reduce that level until we see some reduction or a significant enough reduction in the aeration that we can live with it, and we're not generating a big high pressure within the sump and getting extra oil leaking out through the seals.
And along those lines then, Herb, another one of our attendees asks, how often do you recommend doing oil changes? And what about oil analysis? Yeah, I think you mentioned that briefly earlier, right?
Yes, well, the first time that you change the oil is certainly after you've had a little break-in period on a new gearbox. All those little pieces, those asperites and proud geometries that have broken free and been flushed away in the oil, now they're inside of your gearbox and they're in your oil. And unless you've got a really excellent filtration system, you want to get those out. So after, say, well, it kind of varies by load or by application, but after, say, 100 to 300 hours of operation initially, there ought to be this initial oil change. And then that question really falls down to the application. It varies a great deal. Certainly you want to have periodic analysis at least once a year. I recommend every 6 months that we do a full analysis on any oil sump. But it's also a fact that oil does break down. The additives, the extreme pressure additives, and the anti-foaming additives and the anti-corrosives, those break down chemically over time, and there will come a time when you have to change out that gear oil. Don't expect that it's going to last forever. If you want to be very conservative, think about annually changing gears and gear oil in small sumps where it's not cost prohibitive to do so. Otherwise, you can rely on the analysis of the oil to tell you when it's degraded to the point where it deserves attention and a change.
Okay, thank you. And when it comes to other things in those new gearboxes, right? When do you recommend doing a baseline temperature, vibration, and sound analysis on a new gearbox? Is that something you do immediately after the installation, or do you wait for a certain break-in period and then create the baseline measurements of the healthy gearbox readings at that time?
Typically on a brand new installation, we do want to operate the gearbox at some reduced loading for a period of time if we can. Some applications don't really allow it. But during that break-in process, certainly, we don't want to rely on data that you could collect then to be our baseline. We want to wait till after that. But most modern gearboxes don't require a heck of a long time for breaking that in. I'd say as soon as you're able to operate at full load and speed, it's open season on gathering that baseline data. Better to get it early. I don't like it when folks show up with expecting to do that the moment that we've commissioned and started a unit. Frankly, that's a little bit too much to expect. But after a short break-in period, then you ought to initiate those baseline readings so you've got good data to compare to.
Thanks, Herb. Rob, do you have another one there for Herb?
Yes, so we have another question here from someone listening. It's in regards to proper alignment and soft foot. So it looks like in the field, some people have this issue. How do you evaluate soft foot? How can it affect a gearbox, and how is it typically corrected? And can Philly Gear address soft foot issues on behalf of customers?
Well, soft foot is when, just to define it, that's when we have an unequal loading on some feet or the foundation of a gearbox in some portions of it. How do we find it initially? When we set a gearbox or any piece of equipment, just before you even tighten down the hold down bolts, you ought to go around and consider the amount of free space that you can get a feeler gauge into. If you've got something there, you'll want to take it from all different orientations on that foot, say, so you know whether it's angular or parallel. But we want to fill those gaps until we get sort of a common shared load on all the feet. And then that's sort of the initial soft foot correction. Then we want to carefully tighten those fasteners down, the hold down bolts. And then what I like to do is actually use a dial indicator on each foot. And as I release the amount, or as I release the tension on the hold down bolt, I track how much that foot deflects up from its, I set the dial indicator on 0 and I watch the total amount that it deflects up. I note that down and I actually tighten that fastener back down and move to the next foot. I make an entire survey of the system. And then once I know which feet, when loosened up, jump higher, again, we fill those gaps. And that usually gets us to a pretty good position. What's the problem with soft foot? Well, in gearboxes, especially because we've got bearings that are mounted in the bores of these gearboxes, the housing, the last thing we want to do is rack or twist that gearbox. So we definitely want to avoid soft foot because it can cause angular and parallel misalignments between rotating elements within the gearbox. Yes, we can certainly speak to that. Sometimes soft foot is because of a condition where a machining actually has to occur. It's not just fill in the gaps, it's actually changing the geometry of either the feet of the element that's being bolted down or the mounted positions where each foot lands. Sometimes there's an angular issue, or sometimes there's actually a height problem that needs to be corrected. Another reason we get soft foot is people will install far too many shim elements into a stack underneath a given foot. You know, the rule ought to be minimize that number. 3 is an okay number, but if you've got a stack of very thin shims, well, then you're dealing with a problematic squeezing down of all those surfaces. So that's just one other way to think about and try to minimize soft foot. But yes, we can certainly come in and help you evaluate and correct any soft foot condition on any of your machines. We do it all the time.
Hey, Herb, I had another question come in. It's about baseline measurements regarding noise patterns. The question says, what kind of noise pattern is generated when the gearbox is gradually failing?
Well, it depends on the failure mode. If when we think about noise, you know, that's vibrational energy. We can also think about the vibration that we experience. It depends how it's failing and why. If it's failing in a mode where the surface finish is degraded on meshing elements, then we can get just an overall increase in noise, and vibration will increase as well. But if it's failing because of, say, it's got a cracked tooth or a broken tooth, well, then we get sort of a different signature. Overall, it is a good thing to consider and really get to know your gearbox. As it sounds differently, that's not for no reason. So certainly if you get any sort of change in the frequency or pitch or volume of the sound generated by your gearbox, definitely go investigate it. It's not everything, but it's one more contributing factor that will lead you to further investigation.
Okay, Herb. Well, looks like we're going to end on that note then. Good timing. Thanks very much to you and to the folks there at Philly Gear for providing your expertise during our webinar today. We sure appreciate it. You know, these insights are just the information that we needed in the industry right now. So thanks, Herb.
My pleasure. It's been an absolute joy to speak to you this morning, and certainly do anybody that's online with us, feel free to reach out with questions of any sort regarding gears, and I'd be happy to interact. Thanks a bunch.
You bet. Now, replay of the presentation will be available for on-demand viewing by tomorrow on the website at PTE, and we'll be sending out an email to all the attendees and those who registered so that you can find that link, and you'll be able to share that with your colleagues. And as Herb just said, you know, contact him at hcobb@phillygear.com, or even by phone if you'd like to speak with him directly. So, Rob, thank you. And on behalf of Philadelphia Gear and PTE, we thank you, our audience, for your participation. Great job. High fives all the way around, everybody, and have a real nice day.